Hello everybody, I think I'm ready to get started. So welcome back, I hope you had a good weekend. This week is our next test, it's on Friday, and what I wanted to do, I sent an email to this effect earlier today. Today I want to just talk about the homework material, so we do also have a homework assignment due on Friday, so today I'm going to do some extra examples concerning the homework, which is just about two sections, initial value problems and substitution. And then tomorrow I will just do more examples from like everything that will be on the test, which will include the stuff that's due on the homework this week. All right. Are there any questions about that? The test, is on Friday. I think you know what to expect from the test by now. It covers only the new stuff, that is since exam number 2. We'll talk more about it tomorrow. Any questions at this point about the test? No. All right. Let's just do some more examples from the homework this week then. So there are two sections, the initial value problems and the substitution. I got 2 examples from each of those sections. Let's see if we can do them. So the first one, I just took this out of the book. This is section 7.1, number, what am I doing? 49. I don't know if you care what number it is. It says c prime of x equals x to the 2/3 plus 2, and it says 8 units cost $58. All right. In other words, you could write this way: c of 8. C is the function of which means the cost. The cost of 8 is 58. All right. Got to take my jacket off. It's a little cold down here. Okay, so the cost of 8 units is 58. All right. Your job is to find c of x. All right. So an initial value problem is one in which you are given the derivative. They tell you what the derivative is, which is here, and then they tell you one other thing, which is here, and that other thing is called the initial value. It is one specific value of the function. And then your job is to find the function c of x. What they told us here, this is not c of x, this is c prime of x. We are supposed to find c of x. And the way you do that, if you're told what the derivative is, but you want the original function, is you use the antiderivative. So c of x is the antiderivative of c prime of x. And we can do this antiderivative. The function is x to the 2/3 plus 2. So I'm doing antiderivative of x to the 2/3 plus 2 dx. And we do this antiderivative the usual way. You increase the exponents by 1, and you divide by the exponent. So here I got x to the 2/3. The exponent here is 2/3. I increase by 1. That means 2/3 plus 1. 1 is 3/3, so that would be 5/3 if I add 2/3 plus 1. So this becomes x to the 5/3. That's the new exponent. And out front I got to divide 1 over 5/3. X to the 5/3, and then plus, somebody tell me, somebody shout out, what happens to the plus 2 there? Yeah, it becomes 2x. Thank you for the shout out. 2 becomes 2x. That's the antiderivative of a constant. All right, and then as always we go plus c. Okay, so this is the formula for c of x. Now our job in this problem was find c of x. So this is basically the answer, although there's one last step, which is we have to figure out what the c is. So the last step of this is to solve for the c. This plus c in previous sections has made almost no difference at all. It's just a thing I said, don't forget the plus c. This is the first time it's really been important, is in this initial value problem section. Solve for the c. How do we do that? We do that by plugging in the initial value, or that one other value that they gave us. In this problem, it was c of 8 equals 58. You can see it at the top there. So I'm going to plug in x equal 8 and c of 8 equals 58. So when I plug in here, the left side of this equation is plugging in x equals 8. Instead of c of x, it will say c of 8, which is 58. And then on the right side, we get whatever we get by plugging x equal 8. 1 over 5/3 times 8 to the 5/3 plus 2 times 8 plus c. And this you solve for c. Typically, you're going to want to use your calculator to work the numbers. On our test or something, you will not use a calculator. You'll just, do it by hand. I will choose the numbers so that they work out nicely by hand. What do we get when we do these numbers? So I have my calculator here. I'm just going to do it. I'm going to do 1 over 5/3 is the same as 3/5, and then times 8 to the 5/3. I don't know. Can I even do that on my using my phone calculator? I don't know what all these numbers are. Would you mind if I just looked at the answer? I have the answers in my book, right? It is 114 divided by 5. I don't have a nice calculator with me. I just have this guy here, which is not great for doing exponents and such. All right. I know you turn it sideways, but too many buttons to press. Okay. Anyway, I hope you could do that if you have a decent calculator. And so my final answer is, remember your job in this problem was find c of x. So my final answer is c of x equals, I'm going to write this same formula here, only now I know what the c is. It is 114 over 5. So I get 1 over 5/3, x to the 5/3, plus 2x, plus 114 over 5. And that's my final answer. Any questions about that one? This is a typical initial value problem. All right. Okay, that was sort of an easier one, I guess. The numbers were a little nasty, but let's try one that's a little harder, maybe. I wanted a real word problem from the book, so I have a nice real word problem here that I copied out of the book. It says the number of bachelor's degrees in the United States has been increasing, blah, 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 blah. The rate of change of the number of bachelor's degrees in thousands is this formula here. So this one is going to have some very strange numbers. All right, and the first question, so this is b prime of t. That's how fast the degrees are changing from year to year. And the first question is find b of t, given that this many degrees were conferred in 1970. All right, let's try that. So part A is find b of t. It's just like the one that we just did, where they tell me what b prime is, and then my job is to find what b of t is. So b of t is the antiderivative of b prime of t, right? dt. Hope you don't mind the t variable. Some people only like x. T is fine. Okay, so you just put that formula in here. So this is integral of b prime of t they gave us, 0.06048 t squared minus 1.292 t plus 15.86, right? dt. And we have to find the antiderivative of this. It looks crazy, but actually it's a very simple function in terms of the antiderivative, because we just have powers here. So this coefficient, 0.06048 times 1/3 t cubed, right? And then minus 1.292 times 1/2 t squared. And then finally 15.86 t plus c. All right, that's the antiderivative, and this is b of t. How am I doing so far? Any questions so far? All right, and then it says, remember the question? Find b of t given that this many degrees were conferred in 1970. So that other number, 839,000, whatever, is what I'm going to use to solve for the plus c. So now I'm going to solve for c. And the way that we do that is always by plugging in something. You plug something for t and something for b of t. So we're going to plug. Now it says the time, it says in 1970, but in this problem, if you read the words, you'll see that this problem, the t equals 0 is 1970. So I'm going to plug t equals 0, which actually makes all the numbers work out very nicely. And we plug b of 0, the number of degrees in year 0, which was 1970, is that number up there, 839,700. Now, in the problem, the units here is in thousands. So when I see 839,700, in terms of units of thousands, I'm going to use b of 0 equals 839.7 because my units are thousands. All right. Anyway, let's get it going here. So this b of t becomes b of 0, which is 839.7 equals, and then on the right side, I'm plugging t equals 0 every time. 0.06048 times 1/3 times 0 cubed minus 1.292 times 1/2 times 0 squared plus 15.86 times 0 plus c. And all of these guys are 0, right? All this times 0, times 0, times 0. Those all go away. And I just get 839.7 equals C. So that's what the C is. And I'm ready to write. My final answer is the formula for B of T, but using that number in place of C. So I am copying this thing right here, right? B of T is 0.06048 times 1/3 T cubed minus 1.292 times 1/2 t squared plus 15.86 t plus 839.7. This is my answer. That's the answer for part A. All right. What do you think? Anybody got any questions about that? This is how we do initial value problem. Now, I copied this out of my book, which my book has all the answers in it. That answer, it is actually the same. So as usual, in the back of the book, they simplify things a little bit. So apparently they did this number times 1/3. They actually multiplied that together, and they got this 0.02016, whatever. But those are equivalent answers. All right. All of that was part A. Part B. Let's do part B. It says use the formula from part A to project the number of bachelor's degrees that will be conferred in 2015. I got this out of the old book, so 2015 was in the future at that point. Project the number of bachelor's degrees that will be conferred in 2015, which is T equals 45, year 45. So this one is easy, provided that you did the first part correctly, which I think I did. Part B is just to find how many degrees. That would be B of 45, right? They didn't say it in these words, but they said find how many degrees will be conferred in the year 2015, which is year 45, according to their time scale. How many degrees is just B of 45, and this step involves no integrals or derivatives or anything. You just use the formula that we just found in the previous step here, B of T, right? I use that, but using T equals 45. So B of 45 is 0.06048 times 1/3 t cubed minus 1.29. Sorry, the whole point of this is I'm plugging a value in for t. It is 45 cubed. All right, and then just copying this whole thing. Plugging in 45 for t. There you go. This is my final answer for part B. All right. If you want to, you can plug that into your calculator. It's just a number, you know, and the answer that they gave, apparently they calculated this number is 2,082,000. But that comes from just plugging all of this business into a calculator. All right. What do you think? Any questions about that one? If this were a test question, I would expect you to just leave your answer like I did right there in the red box. All right. All right, those are the examples I wanted to do of initial value problems. Let's try some examples of the substitution, which in my opinion is harder. Substitution. The substitution is a trick for doing the antiderivative. We haven't really learned many tricks for doing the antiderivative, other than just sort of like sometimes you got to distribute or rewrite a division as a multiplication by a negative exponent and then distribute. Substitution is a more sophisticated trick, though. It is based on the chain rule for the derivative. The substitution procedure is kind of analogous to the, you could say it's something like a chain rule for the antiderivative. Let's try an example. I got one that's kind of easier and one that's a little harder. How about x to the 4 times x to the 5 plus 9 to the 3 dx? All right. It's kind of a complicated thing inside the integral sign there. Now, first of all, one thing that you will want to think about, especially on the test, is do you really need to use substitution here, or can you do it some easier way? Now, on the homework this week, in this section, you do need to do substitution on all of them because that's what the whole point of this section. But on our test, I'm just going to ask you to do some integrals. I'm not necessarily going to tell you, you know, hey, by the way, you need the substitution on this one, but this other one you don't need the substitution. So it will be up to you to decide, is the substitution trick necessary here, or can you do it by some easier method? How do you know substitution is necessary? I would say there's sort of two giveaways. One is right here. There's a multiplication right here, x to the 4 times this other thing. And as I've said many times, you cannot do the antiderivative of a product, right? You have to somehow deal with the product. The way we typically would deal with the product is by distributing it. So here you might imagine, why don't I distribute first and then I can deal with it. But can't do that in this case because of this exponent here. You can't distribute something inside of an exponent like that. So this is what should convince you that you need to do the substitution, all right? Now you could, in theory, the exponent itself also is a problem, right? You can't do antiderivatives inside of exponents. When we've seen exponents in the past, one thing that we did was multiply it out, like do the FOIL or something. This you could, I suppose, do. This is the FOIL. You'd have to do it 3 times, which is really a pain. You'd probably mess it up somewhere. But that's the problem. So you should think to yourself, I can't just do this by some simple distributing trick. So I better do the substitution. All right, here's how we do it. You begin by choosing a piece of this to be u. And your choice of the u, there's no hard and fast rule about this, but in general you want to choose something which is inside of something else, inside the parentheses or inside of a square root sign, inside of an exponent maybe. Anybody, any substitution masters out there? What do you think I should choose for the u in this case? Yeah, how about x to the 5 plus 9? I just said, usually you're going to choose the inside of parentheses. So in this example, I'm going to choose x to the 5 plus 9. This choice is really up to you. If you choose wrong, then the rest of it won't work right. And in some cases, you might have to just make one choice and see if it works. If not, go back and try something else. But it's usually going to work what you choose. And then the next step is to compute the du. You have to pick the u out of nowhere. You actually calculate the du by taking the derivative of u. And this you have to don't get it confused what you're doing. To find the du, you take the derivative, not the antiderivative, even though this is an antiderivative problem overall. Take the derivative. The derivative of x to the 5th is 5x to the 4. The 9 goes away when I take the derivative because it's the constant. And then you always include dx as part of the du. All right? So you choose the u first of all. Then you compute the du. And now you're going to try to simplify the integral. So this right here. You're going to try to substitute in stuff to replace all the x's with some things in terms of u's. I want to rewrite the whole integral so that it uses u instead of x. So first of all, I don't know what to do with x to the 4 just yet, but I can definitely replace the thing inside the parentheses here. That is u, and so I'm just going to put u where it goes, which is like that. So x to the 5 plus 9, the whole thing to the 3, that is the same as u to the 3, all right? Okay, what do I do with x to the 4? Well, towards that end, I'm going to, so when I look at this, I should feel like this one, I like that because I already replaced it with a u, and my goal is to replace all the x's with u's. This one over here, I don't really like because it's still in terms of x. And also this one, I don't really like because, again, it still uses x. I'm trying to replace everything which uses x by some equivalent thing which uses u's. So I'm going to sort of gather all the garbage together at the end here. The u cubed, I like the way that turned out already. The rest of it is x to the 4 and dx. So I'm going to write it all together. It turns out this will help you to identify what to do. What should I do with x to the 4 times dx? Well, I see x to the 4 times dx up here is part of the du. It's not actually equal to the du, it's a piece of it, but I can make it equal by dividing that 5. So I'm going to divide 5 over here. 1/5 du equals x to the 4 dx. All right? This is the old dividing the constant trick, which in most u substitution examples you will have to do that, divide the constant over. All right, anyway, all of that was so that I could plug in x to the 4 dx is equal to 1/5 du. So this becomes integral u cubed times 1/5 du. And now the substitution is complete. That is, there are no x's remaining in the integral. I've replaced everything by u's. All right? I hope, like me, you have been writing the integral sign every time here. I keep on writing the integral sign. That's because I never did the antiderivative yet. All of this, all I've been doing so far is just rewriting the inside. All right? And so we have not yet done the antiderivative. One thing that I'll do here, the next step is basically to do the antiderivative, but we have this 1/5 on the inside. That is a constant multiple, and as we have discussed already, you can always pull a constant multiple out of the integral. And so just to make the antiderivative easier, I'm going to bring the 1/5 out front. So the 1/5 will just stay out front, and it will be a multiple on front of whatever the answer is. Anyway, now we are finally at the point when we can do the antiderivative. What is the antiderivative of u to the 3rd? You increase the power by 1 and then divide by the same power. So this 1/5 is just there from before, and then I got 1/4 u to the 4 plus c. All right. In this step, notice I do not write the integral sign or the du anymore. That's because that is the step in which I actually did the antiderivative. And after, certainly after you do the antiderivative, you don't write the integral sign anymore. You don't write the d whatever anymore. All right. Okay. This is basically the end. Although there's always one simple step that we do at the end, because the original problem was stated in terms of x. I should write my answer also in terms of x. And so the final step is always to just replace this u here and write it as whatever it equals in terms of x. So I'm going to fill in 1/5 times 1/4. If you like, that's 1/20. I don't care about that. Times u to the 4th. Instead of u to the 4th, I'm going to write x to the 5 plus 9 to the 4. All right. Since the original problem was stated in terms of x, u was just like a made-up variable in order to do the trick inside there. You should write the answer in terms of x again. All right. And this is the substitution. Any questions about that? This one?
Sorry, Professor.
Yeah, go ahead.
Delayed see how way back when you put the 1/5 du x to the 4th dx,
Yes?
did you choose 1/5 because you have to raise the x to the 4th by 1?
No, it's because, so this formula here, there's a 5,
Okay.
and I'm solving for this part with the bracket around it. And the way to solve for that is to divide the 5 onto the other side.
Thus making it the 1/5.
Yeah.
Okay.
So, like, hypothetically, if it had said something like du equals 8x squared dx, then I would write it as 1/8 du equals x squared dx.
Okay.
It's just
Okay,
taking a constant to the other side of the equation.
Okay, thank you.
Yeah, the fact that 5 happens to be 1 more than 4 is a coincidence here.
Okay, thank you.
All right. What else? These are a little tricky. You got to kind of get used to the procedure. Okay, let's try one more. What do we got? We got integral of 17x over x squared plus 10 dx. All right. Again, you should begin by asking yourself, can I do this without the substitution? Because if you can, it's probably easier to do without the substitution. You cannot do this without the substitution, though. There's no way to divide that. We've done ones with quotients in them, but they always had just a single power of x in the bottom, which we could refactor as a negative exponent and then distribute. That's not going to work in this case because of that. That plus 10 there really messes it up. So I'm going to do the u substitution. I begin by choosing some u. Now, I said before, the u you should always choose to be the inside of something, inside of parentheses, inside of a square root sign, inside of an exponent. I see none of that here. Sometimes it will also work to choose the u to be the inside of a denominator. So in this case, actually this is going to work if I choose the u to be the denominator. There's not really many choices, right? Your only choices really would be that denominator, or I suppose you could try to choose the numerator. You will see it wouldn't work. I'm going to choose the denominator. All right, then, what is the du? Can somebody shout it out?
2x.
2x, yeah, it's the derivative of u, so 2x. dx, surely she meant 2x dx is the du. All right? Okay. Let's try and plug this stuff in. So I'm going to begin by just sticking the u where it is. So this is 17x over u, right? That's the first step that I do when I'm trying to simplify things. You just stick the u into the thing wherever you see the u. In this case, the u was the denominator. Okay, now I'm going to try, like I did before, to sort of separate out the u stuff from the x stuff. I would like to write it so that I'm writing all the u's first, followed by all the x's which are left over. Now, how do you separate out a fraction like that? It would look like this. 1 over u times 17x dx. Right? This is how I would try to separate that fraction out to isolate the 1 over u, which is fine. Like that, I have already substituted. The x dx, 17x dx is the stuff that is a pain to work with. All right? And actually, at this point, we can move the 17 all the way out of the integral. You know, you might worry about, what am I going to do with that 17? Actually, the 17 is not a problem. Because it's a constant multiple can always be moved all the way out of the integral. And so the 17 will just be a multiple on front of whatever the answer is. Okay, what about x dx then? This is the only thing left that we need to worry about. And lucky for us, I see x dx up here. How do I get just by itself? I would divide by 2 there. So I'm going to write 1/2 du is x dx. And so I end up with 17 integral 1 over u times 1/2 du. All right. And as usual, I'm going to move that constant out of the integral also. I have a half on the inside there. We can factor that out of the integral. I'll end up with 17 over 2. Integral 1 over u du. All right. And now this is as simple as it's going to get. Any questions so far? I'm not done yet, but the substitution is complete at least. There are no x's remaining. It's all in terms of u. All right, now we actually do the antiderivative. 17 over 2 stays out front. What is the antiderivative of 1 over u? Any ideas? You might want to refresh your memory. Usually we don't call it u, of course, right? Oops.
Is it ln u with the absolute value?
You better believe it. If this were x, we would say the integral of 1 over x is ln of x. This was one of those rules that we learned for the integral, right? This is the same thing, only it's u instead of x, so I get ln absolute value u plus c, as always. That is the step in which I did the integral, which is why I don't write the integral sign anymore, I don't write the du anymore, and I do write the plus c, because that was the step when I did the integral. I hope, by the way, you've been writing the integral sign all along. I know some people, I saw when I was grading the homework, some people are like integral sign haters. They just don't want to write that thing. You've got to write that thing. If you don't write it, you're going to be very confused, especially at this step, which I just did right here. What happened here? 1 over u turned into ln of absolute value u. It's because I did the integral in that step. And in all these other steps, I was not doing the integral. This is the step at which I did the integral. Okay, this is just about the end. The final step is always replace the u by whatever the u equals in terms of x. So my final answer is 17 over 2, natural log, absolute value, x squared plus 10 plus c. I replace the u with x squared plus 10 because that's what u equals. U equals x squared plus 10. Alrighty. Any questions about that? This is a bit of a harder one. One more thing I wanted to say about this is you can always check your answer on a substitution problem. Yeah, actually, any integral, you can always check your answer by taking the derivative. So this answer that I got, these are related, right? If I did it right, this thing, the answer here, is the antiderivative of what I started with. Said another way, that means the derivative of this answer should equal the original thing that I started with, right? The thing that I begin with is the derivative of the answer. And we can check that by taking the derivative. So I'm going to check it. Here's how you check it. I'll check it in blue. If you have a few extra minutes on the test, I suggest that you do this. You take the derivative of your answer, 17 over 2 ln absolute value x squared plus 10 plus c, right? You take the derivative of that, and if you're doing everything correctly, you should end up with the thing that you started with inside the integral. Let's see if we can do it. What I said, x squared plus 0, it's 10, all right? Let's do it. When I take this derivative, 17 over 2 stays like it is as a coefficient, and then the derivative of the log of something, I'm going to have to do the chain rule. I begin with 1 over x squared plus 10, and then times the derivative of the inside of the log would be 2x. And then plus c becomes plus 0 because the derivative of a constant is 0. Is that the same as what I started with? If you just sort of rearrange things, this 2 down here will cancel this 2. And if I put the 17 and the x into the fraction, this says 17x over x squared plus 10. That really is the same as what I started with, isn't it? This right here matches that, which is why I say checks out, right? This is how you can always check your answer when you're doing the antiderivative. It's a good idea if you got the time. Any questions about that?